Welcome everybody to this talk on Apache Kafka. My name is Daniel Hirsch. I'm a software engineer based in Germany, and I've been looking into Apache Kafka for a while now, and I want to share my knowledge with you so you are able to develop Apache Kafka applications on your own, and so you understand the terms that you face when dealing with Apache Kafka. So let's have a look at the concepts. So which problem does Apache Kafka solve? When you develop any application, when you develop any application of a specific size, of a significant size, then you always have multiple services that interact with each other in some kind of way. Usually you can distinguish these services and separate them out into two categories. Some of the services are going to produce data and some of them are going to consume data. Data producers are, for example, sensors that measure the weather, or it might be users chatting, user messages. It might be images that are uploaded to your application. It might be emails. It might be anything that is produced by some external input. On the other hand, consumers consume data. For example, one consumer would be a database which consumes data that is entered into it and stores it away for future retrieval. Or another consumer might be a social media feed which consumes the latest messages that have been shared. So most big large-scale applications have data producers and consumers, and somehow they need to interact. The data producer has to have some way to share data with the data consumer. And the other way around, the data consumer has to have a way to retrieve data from a producer. Now, in a small application, as in the picture that you see on the slide, this is still relatively simple. You have 4 entities, 4 services, and they share data with each other, and you have four different integrations. Data producer 1 produces data for consumer 1, data producer 1 produces data for consumer 2, and producer 2 produces data for consumer 1 and 2. This results in 4 integrations, but if you increase the amount of producers and consumers, this amount of integrations, the amount of connections between the microservices, it explodes. So that is not a scalable architecture. Ideally, these services should be as decoupled from each other as possible. In this case here, you need to define an API on the producers and the consumers, and it always has to match. You can't change the things, these APIs there independently. You always have to agree on a certain way the data is entered and retrieved. Now, let's have a look at what is event streaming. This is the general concept that deals with this problem of integrations between microservices. And event streaming is basically the following. You have some kind of mechanism, which I highlighted in green here, that accepts data from microservices and distributes data to other microservices. You can think of this event streaming mechanism as a cupboard. Some microservices put things, information into the individual now I have to look up the word great. Some microservices insert information into the cupboard, and some other microservices retrieve information from the cupboard. And not only that, a cupboard is not just a large box where you can throw in information and others take it out, but rather you have certain drawers, and each drawer is responsible for a certain type of information. For example, microservice 1 might put documents into the document drawer, and microservice 4 can open the document drawer and have a look what's inside. Simultaneously, microservice 2 could enter weather data, small cards where the weather and the temperature is written on, into the weather drawer, and microservices 3 and 4 could both look into that drawer and have a look at the information available. And this way, by having this event streaming mechanism in the middle, which accepts data and distributes it again, the data distribution is decoupled. You don't have to specify an API for microservice 1 to access microservice 4. There, you don't need to define this sort of data that is shared between those two, or the protocol. Similarly, you don't have to define any other APIs or protocols or forms of information distribution. Some services just enter information and others retrieve it. So let's have a look at some concepts of Kafka. Kafka is such a drawer. Let's go back to this slide. Think of the drawer as Kafka. That is the point of Kafka. Now let's have a look at what is inside that drawer. On a very large scale, the drawer consists of a broker or brokers. These are practically servers on separate machines or on the same machine. It doesn't really matter. And these brokers, they store data. You can think of a broker as a cupboard where you can enter stuff into and retrieve it from. And entities or services that write into the broker, that put things into the cupboard, are called producers. They produce new information. And services that retrieve information from the cupboard from the broker are consumers. And these brokers, they run on different servers, and you can have multiple brokers or just one. It does not really matter. Also, you can have unlimited producers and unlimited consumers. Now, how does such a broker work? We already had a look at the analogy of drawers, separate drawers, and this analogy applies well here as well. Each drawer you can think of as a topic. You can't just throw bananas and documents and fuel and letters into the same drawer. It has to be separated out to organize things. And this is what topics are for. All messages, all pieces of information that are similar belong into the same topic. So producers, going to the previous slide, write into the broker, and they write to a specific topic, and that can be an unlimited amount of topics. And similarly, the consumers that retrieve data from the broker, they read topics. And what are topics now? Topics could be, for example, messages that people write in a social media environment. So the topic could be named messages or users. And the other topic could be images, something like that. Now, a topic is not just a topic where it's not just a container where everybody can throw in information, but it's logically separated again. A topic can consist of separate partitions. Separate partitions are basically something you can think of as separate folders in a drawer, or on your computer system, different folders. And partitions belong to the same topic, but they separate the information within the topic again. This has a purpose. We will have a look at that later. For example, when users publish messages to Apache Kafka, they send these messages to a topic, and then they can also choose a partition to publish them to. And the partition could be, for example, the first letter of the message. For example, there could be a partition for messages that start with A and go to the letter T, and then partition 2 would go from letter T onwards. And this can also be for other topics, the same thing. Similarly, if the topic would be cars, then partitions could be different brands. Now, what actually happens? A producer writes an event into a topic. Now, here's an example event. The event for a payment system could look like this. There's an event key, that is Alice, a value, made a payment of $200 to Bob, and then an event timestamp. Now, this event could be partitioned by the key, and then there would be a partition for every user or every name, or you could use the first letter of the key or whatever. It's very arbitrary. That can be decided by the producers. Now, what is the purpose of all of that? Since the producers write data into the same topic at the same time, they block each other. I mean, the Kafka broker can only accept one connection at a time for a certain topic. And that's what the partitions solve. The partitions are there to ensure that parallel access can happen. For example, there could be two producers and they write topics into multiple partitions because their messages start with different letters. So different partitions would fill up according to different speeds. Yeah. And what producers write into the partitions are called events. That's what we looked at here. And that's basically it. Now, at the same time, consumers can read these events from the partitions, and each partition can be accessed in parallel. What is crucial here is that the producers can write into the partitions while the consumers can read from the partitions. Why can they do it? When a producer writes into the partition, it appends an event at the end of the partition list. So each partition is a list that stores multiple events, as you see here. And when a new event is written into a partition, it will be appended to the end. In a memory, if you think of physical memory, there will be a pointer pointing to a specific place in memory, and all it has to do is move to the next memory space, write the event into it, move down, write the event into it, move down, write the event into it. So the pointer is basically the index of the partition, and events are written into it. So this is extremely fast and happens completely independently of what is being read from the partition. Because when consumers read something from a partition, they can, or they do, track the index of where they're reading from. So think of the producer pointing somewhere in memory, writing into the memory, And at the same time, the consumer is following up with its own index, and it's reading from a specific place in memory. Then the index will update, it will move the pointer, it will read, and it will move the pointer again and read. And at the same time, the producer is going to produce the information and the consumer is reading. So this is something that happens extremely fast because there are no jumps in memory. This is a big difference as compared to regular databases, where there would be the problem of, for example, in SQL, you can say insert this and this data where this and this condition applies, and then a line of data is written in the middle of the data, and the rest of the data below that entry has to move down. So you would have to move the entire memory to a different place, or you would end up with fragmentation and these memory problems. So these memory segmentation issues arise, but they do not arise with Apache Kafka, and that's what makes it so fast. You can only write to the end, and you can only read from the end. Or no, you can only read from a specific index, and then it updates, and then it reads from the next index. So the consumer reads from the last index it knows, and the producer writes to the last index it knows. I hope that's getting clearer now. Okay. In addition to that, Apache Kafka is completely distributed and decentralized. If we have a look at one of the first slides here, we had the very simple, the simplest possible example of one producer, one broker, and one consumer. The broker is is the entity that contains all the partitions and stores the events for the different partitions and topics. But I highlighted here that there can be also other servers, which would be brokers, and they can exist simultaneously. So when one broker is down, another broker can replace it. And how that it looks like in a running system is that we have one broker, and it knows a part of the data. It stores topic 1 partition 1, topic 2 partition 1, and the next broker stores topic 1 partition 2 and topic 2 partition 2. So these would share the data with each other, and when one broker goes down, it will not all the data is going to be lost. So that's also an important concept here. There are also more advanced topics that we can look into here, which would be that one broker is always the leader of certain topics and partitions, but this would explode the frame, the context here. And that's basically it. That's the presentation I had about Apache Kafka. I hope things got a little bit clearer. And if you like this video, then please leave a like. And if you like this video, then please show it by leaving. And if you like this video, then please show it by leaving a like. Bye bye.